Hello, my name is Jonathan Gashorski, and today I will be showing you how to derive the classical wave equation for a wave on a string. To derive the wave equation, we must first describe our system. So, we must first imagine that we have a person holding a string. And that person is holding a string very tightly, such that there is a tension established in the string. We can further imagine if this person were to take their hand and move it upward. What would happen is the element in the string in their hand would also move upward, followed by the passage of a small amount of time, and then the next string element, and the next one, and the next one, and so on. Eventually, if they brought their hand down swiftly, the same thing would happen. The element of string in their hand would go down, followed by the one after, and so on. And eventually, if this person were to go up and down with the string, making an oscillatory motion, eventually they would make a wave. And that wave can be described by a mathematical function. For example, a sine function is a very common one. And this wave is essentially, well, at least how it's drawn, is essentially a snapshot of the wave in time. So obviously when we look at the wave of a string, it's not going to just be constant where the string is literally completely static in this position. You're going to actually see these crests of the wave moving in the x direction, in the direction of propagation, while you have displacement of the wave, i.e. the amplitude of these crests, in the positive and negative y direction. And as I mentioned, this can be, for example, described by a sine wave. Now another thing I want to say is that the speed of these crests moving, and in short you could say this a little bit differently by saying the speed of these pulses of the string are essentially governed not necessarily by properties of the wave, but actually by properties of the string. So when we think of speed of the wave, or speed of these pulses, we should actually be thinking of rather tension of the string and the linear density of the string instead of wavelength and frequency. Tension, as we have just mentioned, is a force, and that force is established throughout the string with a negative and positive direction. In addition, we have the linear density mu, which it's helpful to know has units of kilogram per meter. These will be more useful to us in a little bit, but to continue with this derivation, we now should describe some of the assumptions that we have in our system. So first, we must restrict ourselves to a system where we think that where the displacement of the string is small. In short, if I were to go ahead and redraw that same wave, our assumption is essentially saying that the amount that is displaced into the y-axis direction, because as you recall, we have x horizontally, y vertically, but the displacement in the y direction must be assumed to be very small. Now secondarily, we must also approximate that the slope of the lines tangent to our string are also small. So there's our tangent line. If we were to go ahead and draw what the slope would be, which is essentially the rise over the run, we want the rise to be very small relative to the run. So in short, we want to just assume that there is a small slope, but that results in a very small rise relative to the run. Third, we must assume that our string is perfectly flexible and that forces of gravity or the dissipation of the tension or movement of the string due to friction doesn't occur. So we just need to assume that our string is perfectly flexible and does not get affected by gravity. So now continuing with our derivation and keeping our focus with the graph on the left side, we can go ahead and label this diagram with forces, and these forces are again a result of the tension that was established in the string initially. So now we can see where F2 and F1 come from. And here we can see that F2 and F1 are not perfectly horizontal or vertical, meaning that they have force components in both the x and y direction given our coordinate system. So we can go ahead and take the graph on the right as our new frame of reference, and seeing how this kind of graph was picked apart, well, we already have dx labeled on the leftmost graph, but if we think of this, this would be our x1, this would be our x2, where delta x is equal to x2 minus x1. And then from there, we can also go ahead and label other portions of this kind of triangle we're building. So if we go ahead and say that this would be our F1, well, the y component of force would be pointed downward, and the x component would be pointed leftward. And where F1x and F1 in general intersect, they create an angle theta. Well, using SOHCAHTOA, we can then go ahead and take the sine or cosine of this, and that would give us either the y component over the hypotenuse or the x component over the hypotenuse, etc. And from there, we can then start building equations for the net x force as well as the net y force. So going ahead and doing that, what we'll have to do for the net x is we'll have to essentially take the tension pulling rightward, subtracting that from the tension pulling leftward, and then for the F net y, the tension pulling upward, and subtract away the tension pulling downward. So what will that look like mathematically? Well, we'll have to first take the F1 of x component, and actually, let me be a little bit more correct here, the F2 of x component minus the F1 of x. And then further expanding that, we could go ahead and see that, well, if I wanted to take F2 of x, what would an equivalence be for that term? Well, if I were to look at angle theta for F2x, in that case, if I were to take the cosine of angle theta, I would get F2x over F2. Multiplying that by F2 affords me an expression for F2x. Now, we do need to label this with respect to where we are on the graph. So since this is with respect to x2, we need to go ahead and say x plus delta x, which is the difference between x1 and x2, and during some snapshot in time. And then we need to go ahead and fill in the space for f of 1x. So then that would be minus, and then exactly the same thing, f of 1 times the cosine of theta, and that theta is the function of x and t. Now, because we've already made the assumption that this is going to be equilibrated in time, this entire expression is actually going to be equal to 0. So f2x is equal in magnitude to f1x. Now to look at f net of y and doing the exact same treatment, what we afford is f net y is equal to f2y minus f1y. And we could further break down these into an expression that is equivalent, which would first give us, if we follow the same logic using SOHCAHTOA, we're actually going to take the sine of this angle, and then multiplying the sine of that angle by the hypotenuse, we'll get an equivalence for f2 sub y. And once again, that theta is a function of x plus delta x and time. And then now we can subtract away the second component, which is f1 sub y, which will then just be f1 times the sine of theta of x and t. Now, because this is not something we made any assumptions about, this is pretty much all we can say about these two equations. Now, one thing I did forget to do for f net of x is we can actually take those equations and set them equal to one another. So what does that mean? Well, if I say that each component of tension is just equal to the tension, no subunit, but just T, and that is equal to F2 times the cosine of theta of x plus delta x. That is also equal to F1 times the cosine of theta, x and t, where all I did was add over F1 times cosine of theta at x and t. So going ahead and doing this, this will actually allow us to make a strategic substitution in just a moment. We can now go ahead and actually look at f net in the y direction. And from here, if we multiply both sides of this, so I'll go ahead and write out the equation first, but if we multiply both sides of this by the cosine of theta over the cosine of theta, otherwise known as 1, we can go ahead and get an expression that looks like this. So then going ahead and adding some brackets here, and we'll put the cosine of theta over cosine of theta. That is multiplied by f2 times the sine of theta, and this would be of x plus delta x at a certain point in time, but to save room I'll just neglect writing that for now, minus f1 times the sine of theta, and that's at x and t. Now going ahead and foiling out the cosines of theta will afford an expression like so. So that's going to be the cosine of theta times f2 times sine of theta over cosine of theta. And then same thing on the right side, cosine of theta times f1 sine of theta over cosine of theta. So now this is our new expression where we can see one trig identity right from the get-go, where sine of theta over cosine of theta is equal to tangent of theta. And it's helpful to know that if we took the tangent of theta using the squares that we were drawing earlier, and let's find those squares. If we take the tangent of theta, for example, on this square that I have shown here, tangent of theta would afford us f of y over f of x. And another way to think about just taking the tangent of theta would give you the rise over the run for that particular force vector. So in this case, we can, instead of writing tangent of theta, we can instead write instead of writing tangent of theta, we can write delta y over delta x. And that would be your rise over the run. And then keeping in mind that this is with respect to x plus delta x in time, and then this one is equal to the same thing, but for x and t. Okay, so let's go ahead and rewrite this expression on the next page, just to make sure we're all caught up on the same place. So then we'll go ahead and write f net y is equal to f2 times cosine of theta times delta y over delta x, and then I'll write it under just to save time, even though this should be written adjacent, minus f1 cosine of theta delta y over delta x, x and t. Now, if we realize that f2 times cosine of theta at x plus delta x as well as x and t, that is actually equal to tau, which we established earlier. So tau here is equal to f2 times cosine of theta at x plus delta x at t, and so on. So we could go ahead and actually make this substitution. So whenever we see f2 times cosine of theta or f1 times cosine of theta, we'll sub in a tau. So going ahead and doing that, and we'll scroll to the bottom and plug that in, this is what we are afforded. We get f net y is equal to tau times delta y over delta x, also with respect to x plus delta x and time, minus tau times delta y over delta x with respect to x and t. Okay, so once we get to this point, we can now obviously see that there is a common factor of tau on both ends. So what we can do with that is we can go ahead and say, okay, let's pull out that tau. So we'll get tau is equal to, or not tau is equal to, tau times the quantity delta y over delta x at x plus delta x and time minus delta y over delta x at x and t. And then that is all equal to fy net. Fy net, if we go ahead and actually break that down, because we know f is equal to m times a, well, and the y direction only, well, what would that be? That would just be m times a sub y, acceleration only in the y direction. Now from here, m and a sub y can both be further broken down. One common one that we should recall is that acceleration, whether it be in the y, x, or any direction, is equal to the double derivative of displacement with respect to time, which in this case, and I'm not sure what keeps happening there, in this case, y is our displacement and dt is our change with respect to time. Separate from that, we could also write a new equivalence for m, where we use the linear density mu, which we should recall is kilograms over meters. So mass equal to mu, which is kilograms per meter, and I'll write that in parentheses. That times some unit of length will give us units of mass, and thus the mass needed for F is equal to ma. So that times what? Well, we're going to go ahead and use delta x there, where delta x is again x2 minus x1, the two positions that we had drawn tangential forces from. And now we can plug in these two new terms into our above expression. So going ahead and doing that, we can see what our expression would look like. So we would have on the left side d squared times y over dt squared times the equivalence for mass, which is going to be mu times delta x. And that's going to be equal to tau on the outside of the brackets times the quantity of delta y over delta x at x plus delta x in a given snapshot in time minus delta y over delta x, again at x, also during some snapshot in time. Now from here, we can go ahead and divide over the delta x that is on the left-hand side and move it on to the right-hand side. And then from here, we must pay very close attention to this right-hand side of the equation. This right-hand side of the equation can be a little bit confusing, but what you should essentially think of here is that when I have this term delta y over delta x at x plus delta x minus delta y over delta x at just x, that's essentially saying the slope at x plus delta x minus the slope at just x. So in other words, within the brackets, we have the change in the slope. In addition, on the outside of the brackets, you can see we have a delta x. So if you couple the inside of the brackets with the outside of the brackets, you can see that we have a change in the slope, or the double derivative with respect to y, the double derivative of y relative to position. So once again, this is almost like the change in the rise with respect to the run. So another way we can actually write this right-hand side of the equation is tau times d squared y over dx squared. Now we can go ahead and return our attention to the left side of this equation, which is just equal to mu times d squared y over dt squared. From here, we could go ahead and make the substitution so that we can have velocity in our wave equation, which is often how it is shown. And what we can do here is we divide over our mu, and using the equivalence that velocity is equal to tension over mu, and that under the square root, well, we can see that if we have t over mu, which is the same thing as squaring the right-hand side of this expression, that would be equal to v squared. So then our new expression for the wave equation becomes d squared y over dt squared is equal to v squared d squared y over dx squared. And thus, we have derived the classical wave equation for the wave on a string.